Excellent. Right, well, welcome to Securi-Tay. My name's Paul. I'm a fourth-year student at Abertay. And we've got this conference today. It's going to be quite a good day. Don't face spam, Rory. Securi-Tay, it's been student-led. Students from the School of Engineering and Computing and Mathematical Science. It started off with the Ethical Hacking Society. Ethical Hacking Society, a very passionate, enthusiastic bunch that make studying ethical hacking at Abertay really good. It's so good to have such a vibrant community to be part of. So we've welcomed the InfoSec community into Abertay today, and it's certainly really good to see a lot of the community come back to Abertay. One of our speakers from last year, Rory McEwen, has came back this year to speak, and it's also good to see people like Securi-Tay, who have came in before to speak to us, coming back today to engage with us again. The program that we've got running, 2 tracks. There's an amendment to the program. Unfortunately, Ryan Ward can no longer speak. So the second track will start at 11:10 with Graham. We've got a Capture the Flag running as well, and Securi-Tay sponsored that very kindly. The first prize of the Capture the Flag is an iPad 2. So certainly there's 7 boxes to pop. On the box will be a key. Get the key, pop it into our website, and if you get more keys, you might win. So I think that's enough from me. A bit of general housekeeping. No fire alarm scheduled for today. If there is one, evacuate, obviously. We've got helpers on the day as well. So any questions of that, please don't hesitate to ask. And I think that is probably enough from me. I'd like to hand over to Nick Walker. Nick was a student here. He graduated last year and then went to work for MWR InfoSec. MWR are one of our sponsors today, and we're delighted to have Nick coming back to Abertay and opening Securi-Tay for us.
Thank you. Am I working? Can you hear me? Yeah? All right, brilliant. Sorry. Right, I've had a lot of coffee today, so hopefully I don't fly through this in 5 minutes. Might have some more. My screen's just gone. There we go. Right, okay. So today, sorry, 1 minute. Can I get this shown on here, please? Sorry. Come on. It's all just disappeared. No? Right, okay. I'll try and carry on without it. Okay, so I'm going to talk today about Android security assessments from a very basic perspective. I'm going to give a short overview on the Android security model, how it all ties together, inter-process communications, the common vulnerabilities that Android is susceptible to that you commonly see in applications that you test, and how to go about identifying those using a tool that MWR has developed that's freely available called Mercury. It's just gone into version 2. So if you're all looking at me like, who's this guy? This is this guy. I'm Nick Walker. Twitter handle's Telossi. I spoke at BrewCon 2011 on Android security, going from WebKit vulns to full remote root code execution. I was here last year? Yeah, last year, as was already said, and I'm now a junior security consultant at MWR. Okay, so the agenda for today, like I said, is a basic overview of Android security concepts, the permissions model, how applications permissions are governed so that they don't affect other areas of the system, common vulnerabilities and misconfigurations that you can commonly see in the applications, and Mercury v2. I've got a demo to show on how one of the aspects of the application work, and that's the reflection interface, which sounds a bit funny, but I promise you it'll all make sense later. Okay, so there are three general concepts when it comes to Android security. Those are the application permissions, the permissions that each application requests at install time. Application sign-in, which is used to verify the integrity of applications and make sure that others developers' applications aren't installed over the top of, so you can't replace applications with malicious ones as long as they're signed correctly. And the underlying UIDs and file access permissions that are, you can see on any Linux distribution. An important part of Android security is the Android manifest.xml, which is basically the configuration file that developers write to decide on, to apply permissions, request permissions from the system, and define all of the IPC endpoints, all of the things that you can use for interaction with the system and between other applications and data on the disk. There's some sandboxing stuff, and as I already mentioned about the Android XML, there's 4 IPC endpoints. So, okay, the sandboxing system uses the standard Linux user and group model to separate functionality between applications. On install time, each application is assigned a unique user UID, so unique user number, as you'll see on a standard Linux distro. And it's assigned groups based on the permissions that it requests. So there's an SD card read group, there's an SD card write group, there's for every single permission there's a group, and you just get assigned to that group if you request a permission. So it's pretty standard underneath. Excuse me. So every process for a given application runs in the context of its assigned user. And communication between apps is done via IPC interfaces. Now, these IPC interfaces are, there's 4 of them, which I'll cover in another slide. The Dalvik VM, which is basically the Java virtual machine that's been developed for Android, is not actually used as a sandboxing mechanism because any application can spawn new processes, and since the NDK has been released, any application can load and run native code, so being in the Java virtual machine doesn't separate you from the rest of the system at all. So, sharing UIDs. On install time and from the manifest, an application can request that it shares a UID across multiple applications. What this means is any permissions that are assigned to that UID are assigned globally to that UID. So say you've got one application that has install packages permissions and internet access. If you then set up a second application that you only want to have, I don't know, SMS read access, but you set up a shared UID, that application will actually have an effect on the underlying system, SMS read, install applications, and internet permissions. So you have to be careful with that kind of thing. So. IPC and activities. So the way this works is all the IPC interfaces are all boiled down back to the binder driver on the underlying system. And now what's the binder? The binder's a device driver and daemon which deals with IPC requests and routes them to the respective applications. So the 4 different IPC endpoints you can get are services, broadcast receivers, content providers, and activities. And all of those communications occur by special packets, local Unix packets that are intents. They can contain objects for the Dalvik VM, they contain arguments, and they contain the URI, which is that needs to be routed to. So let's go over the 4 IPC endpoints and kind of get a feel for what they do, why they're important, and what their impact on the security of the system is. So, services are the non-visual components of the app. Anything that you want to do in the background, I don't know, something that you don't want to slow down the UI with, is set up in a service. Now, any services, any application can bind to an exported service and use the methods that are exposed by it. And what I mean by exposed is if it's declared as public in the Java code, then any application can bind to that service and execute those methods. As I said, the services are defined in the manifest, and the attributes of that service are also defined in the manifest. So the configuration options that are going to be applied and the security and the permissions are going to be applied by configuration options in the Android manifest. So the various attributes that you can apply are the exported attribute, which basically says whether other applications other than the one that you write in can see this service. The default value for a service is false, which is important, but it can be implicitly exported. Now, what does this mean? It'll make more sense after I say the next one, which is permissions. The permissions required to access. If you set up a permissions filter, which says in order to see this service, you need to have the, I don't know, Android SMS read permission. The second you apply a permission to that service, the service is automatically exported unless you've explicitly set the exportation to false. So it catches a lot of developers out, and we commonly see exported services just because they've applied permissions to it and not realized. The process is obviously the name of the process ID that you want the service to run in. Okay, so content providers, arguably the most important one because it's the one that mainly deals with the data on the phone. So content providers, they supply the data and the information to each application. It's like a global interface to stuff on disk or dynamically generated. So yeah, data can be stored on disk any way you want. Realistically, you can wrap a content provider around any type of data that you can think of. You just have to overload the embedded content provider. You can generate data dynamically, programmatically, but the most common implementation, I would say probably 95% of the stuff we see is SQLite-backed content providers. So again, attributes are defined in the manifest, and a big important point, the 99% of the time this vulnerability rises because it's export true by default, and developers don't know this. It's the only IPC endpoint which is exported by default, and it's arguably the most important as far as security is concerned because it deals with all the user data. So that's something definitely to look out for. If it's exported, any application on the system, regardless of permissions, can connect to it and just start pulling data off. Okay, so there's two separate permissions, read permission and write permission. They do exactly what they say on the tin. Permissions for access to data and permission to modify data. There's a permission tag you can put in which sets both of these at the same time. It's basically a cheat. And if you set a read permission and a write permission and then a permission, the permission overrides the other two. So occasionally you'll get a misconfiguration whereby you set a read permission for some low privilege thing and a high privilege write permission, and then you set a misconfiguration where you get a low permission and the low permission overrides the write permission. So broadcast receivers. Broadcast receivers are an IPC interface which allows you to catch system-wide events. So they process and react to broadcast messages that are sent out from the binder daemon. So they often originate from system, but there is nothing in the system that says I am an official broadcast message, and applications can send arbitrary broadcast messages. Some system events can only be received by applications with specific permissions, such as a good example is the SMS read one. When an SMS comes in, broadcast is sent out to the whole system, and the binder sees which applications have the SMS read permission, and only they will receive that broadcast event. Again, defined in the manifest, attributes are exported, false by default, but it can be implicitly exported, again, when you apply permissions. that implicitly exports the application. So the main points to think about so far are content providers, exported by default. All the others aren't exported, but the second you apply permissions, they become exported unless explicitly told otherwise. Biggest mistake you see in an Android application. Okay, so activities. Think screens. They're the visual components of the application, but they're not visual only. It's the code attached to those visual screens as well. So they can be started by other applications if exported, and they're defined in the manifest. So exported is false by default again, the permission defines what's needed to start the activity. Aliases, they're another important point. What they do is you can set up a sub-activity, which is basically an alias for the first one. So any intents that get passed to a specific activity also get forwarded to the alias, so a second activity. And the alias overrides if you set up an alias, the alias overrides the attributes of the base activity. So if you have an alias activity that's exported, and you think your original activity is not exported, if you set the alias up, then the exported attribute will be overridden on the original. Okay, so I've pretty much already covered this, but only exported IPC endpoints can be accessed by other applications, and content providers are exported by default. Big problem. Keep an eye on it. So developers can explicitly export via the manifest, and services, broadcast, received, and activities can be implicitly exported based on the permissions. Okay? Any intent filter, permissions filter, application filter will lead to implicit exportation. And all apps are able to interface with the endpoint when no permissions are set if it's exported. Okay, so applications have no permissions by default. What does this mean in real terms? It means that in order to use any functionality that would either A, affect other applications, or B, affect data that affects the user, you need some sort of permission. That's the overall general idea. It's not always the case, but that's the underlying kind of idea that the Android system's built around. The permissions, again, are requested at install time via the application manifest, and they look like Android permission.receive SMS. You can define arbitrary permissions, your own custom permissions, and define what they mean. Yeah, cool, I covered that. Okay, so what is the attack vector on a phone? What sort of things can attackers do? What access do they need to have any kind of impact on the applications itself and the integrity of it? So any malicious user on the same network as the device, let's see what kind of, any traffic shaping, traffic changes, what can that do to that device? A malicious user with non-privileged malware, which is probably the most common threat and probably the most important to try and consider when you're doing a pen test. Or a malicious user with root code execution on the device. With the kind of landscape of Android, you get a lot of root code execution vulnerabilities with the jailbreaking kind of scene that you see on iPhone. So this is not, a malicious user with root code execution on a device is not really too out of the way, you know? Okay, so quick overview of the common vulnerabilities you'll see. I'm not really going to go into massive detail because for each of these, there's papers and papers and papers everywhere on each of these. So generic Java issues. Obviously, Android applications are written in Java for the Dalvik VM, and it falls privy to the same kind of bugs that you see in any Android application. Runtime.getRuntime.exec with user input, so running system commands, or serialization and deserialization of objects that are passed over a network. Losing state between activities. What is that? That is when an activity, say you've got to go through a specific process, for example, a password reset process in your application. Because you can start activities via intents, you can essentially skip over the top of things. So an application that needed a password reset mechanism where you had to answer a secret question, if you can call the intents out of order, then perhaps you can call the password reset activity before you've answered the secret question and just reset your password, things like that. But you actually see that quite a lot because developers, for some reason, like to export their activities rather than leave them by default unexported. Okay, another big issue, probably the biggest issue, is excessive and misconfiguration of permissions. Developers are lazy. They request everything that they can so that it saves them headaches later. And that's not the way to write a secure Android application. The amount of applications I've seen with install applications permissions, and they're just like, I don't know, some banking application or some rubbishy interface to a web app, and it needs install permissions for some reason. I don't think so. So if someone finds a vulnerability in your application and manages to get some sort of functionality, control of some sort of functionality within your Android application, they get those permissions. You don't want to give that sort of granularity and control to an attacker, especially install applications, because it's basically a free pass to all the permissions on the device. Because if you install an application using another application which has install permissions, the user doesn't see anything. You just request all the permissions you want, and suddenly it's on the phone, and you've got all of those permissions under your control. SQL injection in content providers. Like I said, content providers are backed more often than not by SQLite, SQLite 3. And it falls privy to the same kind of SQL injection problems that you'll see. It's a little bit strange on Android because the default query operation, the default query method that you can use to speak to a SQLite database content provider on Android it's parameterized, but still vulnerable to SQL injection because there are multiple parameters. The only parameter that's parameterized is the final parameter that's user supplied. But if there's two other parameters before that which define the table name and the restrictions on the selection. And those are called projection and selection arguments. And they are not parameterized, and occasionally you'll see an application where those are derived from user input, and you can get SQL injection via that. Bugs in native code, as I said, you can run, the NDK allows you to run basically C on the device. And they thought that you get the same memory corruption vulnerabilities that you see anywhere else in an unmanaged language. Poor data storage. I'm talking about encryption, protecting the user's information from other applications on the device. Now, you can't rely on the Linux file permissions to do that. You need to have some sort of encryption on your data if it's sensitive at all, because again, like I said, with Android, you get a lot of root command execution vulnerabilities, and root command execution vulnerabilities don't care about your permissions. Network integrity. If your application speaks to a backend web app, it needs to enforce HTTPS on all comms and implement certificate pinning, which isn't supported by default on Android. What do I mean by certificate pinning? I mean only accepting one specific SSL certificate or small range of SSL certificates. And in order to implement that, you need to implement your own, overload the default trust manager, which is the SSL handler on Android, and you instruct it to only accept one specific certificate. There's documents all over the net about that. Moxie Marlinspike has done a really good article because there's a couple of methods to do it. Poor data storage. I think I've already done that one, have I? Okay. Information disclosure. Login is the main culprit for that, or crash logs. The amount of times that an application is done perfectly well everywhere else, the data is encrypted on disk, everything's done over HTTPS, but then you can see the HTTPS URL going out with the parameters in it in the log. It kind of just defeats the point. And use of WebKit. A lot of people will argue with me for this. It's not widely accepted as a vulnerability. But you can, inside an application, you can embed the WebKit rendering system. So you can pull in web pages and have them rendered within the context of your application through WebKit. Now, what happens if some attacker's sitting on the network, same Wi-Fi as your Joe Blogg's using your application in the corner, and you go to some web page, he's intercepted your traffic and stuck a WebKit vulnerability, injected a WebKit vulnerability in JS to your page. It comes back, crashes your application. He's got command execution within the context of your application's permissions. Okay, so say you got install permissions, he gets command prompt shell back, he's got full control of your phone just because you use WebKit. All functionality that you need to use WebKit for can be done via the default browser, so that they click a button, takes them to the default browser, so that then the application, that if it gets exploited, only has permissions of the browser. And then you can click a link inside the web application that brings you back to your application. So there's no reason at all not to offload all of your WebKit stuff to the default browser. It just gives more of a access to your device if someone gets control of it. Debugging. Debugging flag is set more often than not because developers forget to turn it off. When you build an Android app in Eclipse, the default configuration leaves the debugging flag on unless you explicitly turn it off. And what that means is that any application, when it starts up, when it's got the debugging flag set to on, it tries to connect to a local Unix socket on the device, which anybody can bind to. So if you've got debugging flag set, and a malicious application starts up and says, right, bind to this JDWP socket, which is the Java debugging socket. When they start an application up, the application connects to the malicious application. You got full code, like code injection, full debugging on the target application. Okay, so what's the testing process? How do you begin to look and start rooting out these vulnerabilities? I'm not going to go into a massive static analysis versus dynamic analysis route because, to be honest, there's not a lot of dynamic analysis stuff on Android. I'm going to demo some stuff later. So what do? You download the target application packages that you want. You examine, you extract the application manifest. So an APK, which is the installer kind of package for an Android application, is basically a glorified zip file. You could extract it, pull out the Android application manifest, and you can decompile the DEX files into source or bytecode. It depends on the configuration of the application. There can be some obfuscation there. Occasionally it's a little bit difficult, but more often than not, you'll get back to pretty realistic source code. So with that, analyze your manifest to see what configuration options have been set. You can immediately tell straight away whether it's going to be a good or a bad test based on what's exported, what's not. Analyze the code, look for the SQL injection vulnerabilities and things like that I mentioned. See if you find what you think seems to be a vulnerability. You've got to test it. You've got to verify that vulnerability exists. So how do you do that? You have to write custom applications for each vulnerability that you find to try and connect that content provider and try and extract information. You don't know whether that vulnerability exists. It looks like it does in code. Does it actually in practice? So this whole process requires loads of different tools, JDGUI, DEX to jar, all sorts. There's tons of stuff that you need to do this. And it's slow. For testing every vulnerability, writing a custom app and kind of doing that sort of thing statically it's a pain in the backside, to be honest with you. So enter Mercury v2. What is that? It's a framework for performing security audits and against applications and the underlying Android system. It's an exploit development framework, kind of like what you see in Metasploit, but for Android applications on the system. Sorry, one sec. Okay. It was used as the payload in the Samsung Galaxy S3 pwn2own exploit, which was full remote control over a Samsung Galaxy S3 with full permissions from NFC. It's written in Python, and it dynamically interacts with IPC endpoints. There's a framework and a structure in place that lets you, rather than keep writing the same code to kind of test that these vulnerabilities exist. You can dynamically just say, I want to connect to this content provider with this URI, and I want to give it these parameters. Please give me the output. It'll drop you to an interactive system shell, so you're not always in like kind of Java context, VM context. You can go to a system kind of command execution context. And it supports full scripting. Excuse me. You got full file transfer, searchable modules, tab completion, same thing you'd expect in any other kind of pen testing framework. And it doesn't require ADB. The demo I'll be using today will connect to over ADB through TCP port forward and the ADB supports, but it can connect completely over the network. And it's got an infrastructure mode whereby rather than having one client connection to one physical phone device, you can have a connection to a server, which in turn has loads of reverse connections to multiple devices. So you can test against, say you've got to do a test against, I don't know, 2.1, Jelly Bean, and I don't know, some weird tablet that you've never seen before. Just stick an agent on each of them, connect them to an infrastructure device, and then you can control them all and do and run the tests across all of the devices at the same time. Okay, so what does it look like? Well, this is running an SQL injection test against stock. SGS2 is vulnerable, and it was patched in SGS3. So this is, I don't know if you guys can see that, but it's just checking loads of different applications that come installed by default on the SGS2 for various known vulnerabilities. What sort of, how am I doing for time? Okay. So these are the kind of, all of the modules are separated into namespaces. And these are the main namespaces that you can see. The package namespace, where you can get information about installed packages. You can automatically scan the attack surface. So if you run package.attack surface module, it will scan the application that you give it, and it will say this, and this is exported, and this one requires these permissions. So you can immediately enumerate what is externally facing to a non-privileged application as the agent on the device. The only permission it has is the internet permissions, and that's to use the socket to connect back to the servers. You'd be surprised what you can see on an Android device with absolutely zero permissions at all. So the activity namespace, you get information about exported activities, get a list of intents, send those intents out, and start activities from Mercury. So you're sitting, from your Mercury console, you can pop up different screens on your Android device and send arbitrary data. If they take arguments, you can send arbitrary data in those intents and pass stuff to the methods that are on that activity. Broadcast, get information, there's not much to those. Get information about exported broadcast receivers and the permissions they require, and send arbitrary broadcasts out. So not just the system can do it, as I said, any application can do it if the code is there to send out that broadcast. It's just an intent packet that you send out. The provider namespace is where you can determine information about the content providers used by any application or all applications. Each of these namespaces you can run against the whole system or a specific application, or things that meet a certain things that match a certain regex pattern. There's loads of different bits to it. You search for the URIs in the packages, so it'll get a package, it'll scrape it, it'll search all the way through it, and it'll find out all of the URIs that application references, so you immediately know what tables are in the databases and what sort of data that application is working with. You can connect to those content providers and send arbitrary SQL. If the permissions are set up right, the SQL won't work. If it's done up wrong, you'll get all the information back. Services, same thing as the other ones. Enumerate the service and permissions they require. Start and stop the services. You can attach to services. Exploit modules are modules that have been written to exploit existing vulnerabilities, known vulnerabilities. There's not a huge amount of those in the system yet. There's a lot of stuff for the SGS2 and SGS3. We've got some ZT device things. We've got some privesc modules that return root shells on various devices. But because of the way the Android ecosystem works, the kind of pretty device specific. It's very rare that you'll find a vulnerability that affects a wide range of Android devices. Tools, various utilities that you need for doing your test, MD5 summon files, file transfer, setting up BusyBox. Because there's not a lot of command line stuff built into Android. You have to add that kind of functionality in yourself. And handily enough, there's one executable called BusyBox, which has got loads and loads of functionality built into it. The one on Mercury has actually got extra functionality in it than the default one that you'll generally see on Android. You won't generally see Netcat embedded into the ones that you'll see on the standard routing. If you root your device, you won't actually get installed BusyBox. And generally, it's kind of a chopped-down version of BusyBox that doesn't have all the functionality in. The one on Mercury is the stock BusyBox with all the functionality embedded in it, so you can do Netcat reverse shells and stuff from it. You can do anything you want. It's got a full, it's like the full GNU toolchain with extra bells and whistles. You can drop to a persistent shell or run one-off commands. It's got all the PrivS modules currently return shells, which is awesome. You can do most things on the device, but you can't currently do anything in the Java context from that. I'm currently I've got a research project at the moment where I'm trying to, rather than return root shells, I'm going to be working on returning Java code execution with root permissions. And there's one auxiliary module right now. We're looking at adding a few more. But the auxiliary module that we've currently got is the Web Content Resolver, which basically is a web service interface to all of the content providers on the phone. It searches for all the content providers on the device and sets up a wrapper so that you get given a web interface and you can run SQL map and things like that against the content providers. So you can use your standard tool set against what would normally be quite a quirky thing to work with. So what is Mercury under the hood? It's a Python thick client and a tiny, tiny Java agent. There's, I say, minimal hard-coded functionality. As of Mercury v2, there is no hard-coded functionality. It's purely reflection-based. I'll explain what that means later. It's got client-server, it's got infrastructure mode, and it'll do reverse, as we did for the payload in Pwn2Own. And the network protocol between the agent and the client on the PC is XML-based and requires one privilege, so you get a really good, realistic view of what kind of access you have on the phone with non-privileged malware. All functionality now is provided by the reflection interface. So what is that? No support in Mercury v1. It came in Mercury v1.1. Has anybody used Mercury? It was publicly released. A couple, not many. Right, cool. Well, maybe after today you'll give it a shot. If there was an issue with it, with Mercury v1, where if you wanted to do something slightly out of the ordinary and the agent didn't support it, it sucked. You had to modify the agent, rebuild it, reinstall it on the device, and basically blow up the application. And what you want on the phone, on a small device with limited processing power, you want something small and dynamic. Some things were way too slow. For example, Secret Codes API module that we've got. You get like the star hash, blah, blah, blah numbers, hash, and they do certain functionality on the phone. We've got a module that goes through all of the packages on the device and extracts all of those secret codes and tries to figure out what they do. And that on Mercury v1 was tediously slow. And by tediously slow, I mean you needed the phone plugged in, otherwise it would die of battery before your module finished. Okay? So original Mercury v1 had a few teething problems. And we needed a way to, rather than have all the functionality that we needed already on the agent, we needed a way to say, hey, agent, run this code, please. So we needed a way to instantiate new Java objects, access their fields, call methods, and set the properties. Java supports reflection, which is awesome. It's your ability to inspect classes, objects, call their methods, enumerate the properties, all at runtime, inline. Okay? So you can ask an object about itself. You can say, hey, what methods have you got, what properties have you got, and it'll speak back to you, it'll say, right, I've got this, I don't know, length property, and I've got exec method, which is really handy. So we started making the reflection interface, whereby it's a way to write code in your Python client, so write raw Python code and have it executed as Java on the agent. So Mike Orty and Nils at the office sat down one day and said, right, we need to get this functionality sorted out in Mercury. So they sat down, they came up with a spec, a network spec, and the 7 methods that we need. So the 7 methods are resolve. It takes a class name as a string and resolves that back to a class. Construct will take that resolve class and create an object of it. Invoke lets you call a method on an object. Set prop and get prop, or get and set properties like your length attributes and various other things you can have, arbitrary ones. Delete, simple, forget about the object, and delete all, forget all the objects. So how does this work under the hood? How does the reflection interface work as with the context of the client and the server? So when a new object is created on the agent, it tells the Python client an ID. I've got this object, you just need to know it's got this ID. So both the client and server know that objects exist now, so now we can say, hey, agent, run this method on this object that has got this ID. So both client and server can now speak back and forth and they know about what is being executed. Okay, so that was awesome, but for a small number of tasks, reflection code sucked because you had to write a big chunk of code to get a little bit of Java code working. So there was loads and loads of round trips because for every method or object you wanted to create, you had to go from Python, you had to say, hey, I want this object. All right, go across. The agent would say, right, here's this object, here's the ID. And there's a lot of back and forth in for every single kind of operation you want to do for one line of Java. You've got essentially 2 pieces of network traffic, which wasn't ideal. So Mercury v2 added a class load method to the reflection interface, where using this, you can write standard Java code in Eclipse, compile it to a class file, and using the Android SDK, convert that to a DEX file based APK, which is a tiny, tiny piece of code. It's basically just a class in a zip file. That's all it is. And then using the Python client, you can say, hey, take this APK and reflect it onto the agent. So it goes across the wire into the agent. The agent calls class load on it, and that's basically an object is created based on the APK you use. And that way you can seamlessly call the methods on the code you've created. So you can write some, I don't know, really lengthy function that you want to reflect. And you just send the whole APK across, get an object at the other end. So you've got one piece of network traffic. And then from Python, you can just say, call this method, call this method, call this method, and just do all the functionality that you want. Since v2, full rewrite from the ground up. All the functionality is reflected and class loaded. The network stuff is done through a class loaded APK. The file transfer up and down is from a class loaded APK. There is no functionality in the agent except for the reflection interface. So, right, demo gremlins, come on. I've got to do a reflection demo. This is Java code to run a single command like in a shell. Okay, so you got to get a runtime, and then using that runtime, you execute your command. You get the output of that command using a buffered reader and input stream reader, and then you read the lines back. Okay, let me just get set up here. Okay. Let's see if I can Mercury console connect. Please. Oh, bugger. Right, hold on. Oh, yeah. I've not enabled the server, that'll be why. Okay, so this is your Mercury server. Tick the box. Yay. Okay, so you can get rid of that. Mercury console connect, please work. Yay, right, so you get a Mercury prompt. Can everybody see that properly? Cool, right. So what I've done is I've written one module that literally just drops me to an interactive shell so I can show you this reflection stuff line by line. So if we do run scanner .misc.demo, please, yes. Okay, so I'm in a basic Python interpreter. So in order to use the reflection interface, we need to get the current session's reflection object, which is basically your interface to the whole reflection API that we've developed. So if we do get a ref object equals self.reflector. Okay, so we've got a reflector instance that we can work with now. So we need to do, as you've seen, can we get the slides back? Okay, so now we need to get the runtime and run exec on it, and that returns a process. Okay, so we'll do runt equals ref.resolve. So resolve that class to a name, java.lang.runtime. Yep. And then what that'll return is an ID based on that object. And because Python knows that that's a reflected object and that it needs to pass any method calls that are placed on that object to be executed on the agent, you can literally just call .getRuntime, even though that method's not defined in Python, because Python knows that it's a reflected object and it doesn't need to actually do that method in Python. It should pass that off to the agent. So what will get returned to this will be the result of getRuntime. Python won't actually get that runtime back. It'll get an ID that refers to the runtime on the device, which is an actual object. Okay, let's see what we got back was a reflected object, which is, as I said, just an ID, an interface into it. So next thing we need to do is call exec, get a buffered reader, and set up get the output stream of the command. So we get a process return from that. Runt.invoker. Exec. ID. I think that's right. Yep. So we should get another object back, a separate reflected object. Yep. So now we need an input stream reader, which takes as a constructor argument the input stream of the process. So as I said, you can just call those methods on those fake reflected objects. So you can do input stream reader equals self.new java.io.input stream reader. Sorry, my typing is awful in the morning. proc.get input stream. Okay. Okay, so we've got the input stream reader resolved and constructed at the other end with the arguments got back from the input stream. Now all we need to use is construct a buffered reader based on input stream reader and then call readline on it. So if we do br equals self.new java.io.buffered reader, and then takes the input stream reader object as an argument. That should give us a buffered reader back, and we can do br.read line. And you see the command being executed in the Java context from Python at the other end on the agent. So if you don't, in case you don't believe me that this is actually being done in Python, if I do something like, I don't know, call a method on something that doesn't exist. Buffered reader doesn't have a method foo, and what you get back is a java.lang.no such method exception. So it's actually being run in Java in real time at the other end. So back to my slides. Oh, yeah. So what you can, again, you could do that whole thing in an APK that you can class load, or you can actually do all those inlined. I've actually got another module, actually, I'll show you this. Exit. Right, if we do run scanner misc reflection test, this is basically a pre-written module that basically wraps all those commands up and runs multiple commands in line. So you can use that stuff that you've just learned to write arbitrary modules like this one that spams your screen and moves too fast. Okay, so you can see that I ran an ID and I ran ls, and I kept reading until I got a reflected null object back, which is basically what BR returned. Okay, so that's the end of my talk. I don't know whether I've done well on time, but Mercury v2 is available from our labs page. There's downloads, user guides, a big blog write-up that Mike did on the creation of the reflection interface and the stages we went through, the problems we hit. There's the tutorials on that, and there's a development blog that says kind of how we moved along. So, you guys got any questions for me? Keep it easy because it's early in the morning. Yeah.
Is this something you're seeing more often than not now? Android exploits coming out of the world?
You tend to see the same problems in most places, which is exported content providers and excessive permissions. Those are the two main ones. And nearly every app that uses HTTPS never uses certificate pinning, so it's basically moot. Those are the vulnerabilities that we tend to see. So, anything else? No?
No more
Cool.
questions, Thanks for watching.
No problem.